All right, so in this circuit, we've got a battery, resistor, and then this parallel block of resistor, capacitor, and then moves back to the battery. At time zero, what are we assuming about the capacitor?
It's not charged.
It's not charged. We're assuming capacitor is empty. Q initial equals 0. And so what we want to do, we want to figure out what does the circuit act like when the capacitor is empty. And the important thing for that, I think, is really the delta voltage. What would be the delta voltage of the capacitor if it has no charge at all?
Zero.
Zero. An empty capacitor provides no pushback whatsoever. And the important thing about these paths is these paths are in parallel. What has to be true about the voltages of parallel paths?
It's the same.
All the same. So if this capacitor is 0 volts, these resistors are also getting 0 volts. They have no voltage difference. On a capacitor, no voltage difference means no charge is stored. For a resistor, though, what does no voltage difference mean?
No charge is flowing through it?
No charge is flowing. There's no current. If you've got a resistor and you've got, like, let's say on one side the voltage is 3 volts and on the other side the voltage is also 3 volts. No delta voltage means no current at all. This path may as well not even be there. So that's what we can do for time zero. At time zero, there's no voltage on the capacitor, which means no voltage on these other branches of the parallel network as well. And no voltage on a resistor means no current.
This was kind of like a side question, but if we do have an uncharged capacitor and they aren't like in parallel or in series with other resistors, what would we like consider that, I guess? Like, would it short out anything?
Yeah, this is effectively shorting it out. Because the capacitor having 0 volts, what's another circuit element that always has delta V equals 0?
A wire.
Right. So this capacitor is temporarily acting like just wire. And if we had something like that, if we did just draw that as just wire, if we actually drew in the capacitor as just wire, this wire acts as a short circuit. That the current going through here, usually we'd expect the current to split 3 ways, and whichever branch has less resistance gets more current, and the ones with more resistance get less current. In this case, though, if you've got a branch that has 0 resistance, no pushback at all, then none of the current goes through the other branches. All the current goes this way.
Yeah, but I was wondering if I guess like the wire in this case, like the uncharged capacitor was in the circuit and there were resistors, but it wasn't necessarily in parallel or in series with any of the resistors. Like, would we say that it can short out anything or it wouldn't?
Well, the empty capacitor acts as a short in the sense that the empty capacitor acts like just wire.
Okay.
So what you want to do is if the capacitor is empty, try redrawing the circuit with the empty capacitor drawn as just wire. And ask yourself, would that wire cause any resistors to short out?
Okay.
Would it cause any resistors to have 0 voltage difference is really the important thing.
Oh, okay.
Like in this case, this branch is in parallel with these branches. So all 3 of them have to have the same voltage. So if one of those branches has 0 volts, the other ones also have 0 volts. And therefore no current flow. So at time 0, we know that these resistors are getting no current at all. So R2 and R3 are shorted out. But of course, current is still flowing. Current is going to flow around this path. But since these 2 resistors have no voltage and therefore no current flowing through them, these 2 resistors may as well not even be there. If we just imagine removing those, we haven't actually changed the current. So we can just erase those and treat this region as the entire circuit because that's all the current is flowing through. And at this point, this now acts like a circuit with just the battery and this one resistor. And that's it. So if you have a 40-volt battery, and now this R1 is the total resistance because the other resistors are no longer part of the circuit at this instant in time. So our total is just 3 ohms. And then how would you find the current? How would you usually calculate current in a loop that's just a battery, a resistor, and nothing else?
Use the loop rule.
Yeah, loop rule would be that those delta voltages add up to 0. Delta V battery plus delta V of that one resistor add up to 0. We could fill in the usual epsilon for the battery and the usual minus IR for the resistor. Solve for I, and what do you get? How would you isolate I in this equation?
Would it be 40 over 3?
Yeah, or more generally, epsilon over R. And you can actually use this as a general formula for anytime you've got a single loop with just one battery and one resistor and that's it. And anytime you have a circuit that's exactly that simple, the current is always going to be epsilon from the battery divided by R from the resistor. In this case, yes, that would be 40 volts over 3 ohms. 40 thirds is 13 and a third. So 13 and a third amps. That would be the current at time 0 through the battery and R1 and the capacitor, but there would be no current through R2 and R3. So we got I equals 13 and a third amps through the battery and R1 and the capacitor as well. And I is 0 amps through R2 and R3. So that basically tells us everything we need to know about the current or the state of the circuit at time 0. Any questions on that so far? Then let's take a look at what's happening after a long time. After a long time, that is as t approaches infinity. So we're assuming everything has gotten close enough to its asymptotes. And this might mean a few seconds later or a few minutes later or a few hours later, really depending on what the half-life is and how close is close enough. But after a long enough time, what should we assume about the capacitor? What's going to happen to the capacitor as time passes, as current flows through it?
It gets fully charged.
Yeah, the capacitor is going to get charged up. And it gets more and more charge. So the positive terminal of the battery links to a plate that's going to become more positive. The negative terminal of the battery links to a plate that's going to become more negative. So the capacitor gets more and more charge, but as it fills up more and more, what happens to the current through the capacitor?
It gets closer to 0.
It gets closer to 0. The more charge builds up on the capacitor, the more the capacitor pushes back against the push from the battery, and the more difficult it is to cause current to flow through the capacitor. So the current through the capacitor gets weaker and weaker, eventually approaching 0. In fact, if the current is not 0 yet, we would say the capacitor is not yet full. It's still in the process of filling up. For the capacitor to be full, capacitor is full, meaning
Easy.
the current in the current flowing through the capacitor has stopped.
Casey, can you explain why there's like the plus charges on that side and then the minus charges on the other side?
Yeah, if you take a look at the battery itself, the battery, on the battery, the notation we use is the long bar represents the positive terminal and the short bar represents the negative terminal. So the positive terminal creates positive charge on the plate most directly linked to it. The negative terminal creates negative charge on the plate most directly linked to it. Okay. If you look at what's going on microscopically, the negative charge is, since the electrons are what's able to move around, the negative charge pushes electrons away from itself, and those electrons end up on this plate.
Oh, okay.
The positive charge pulls electrons in, which means this plate is losing electrons, and the positive charge is what's left over when some of the electrons leave.
Okay, got it.
You could also just think of that as the direction current's flowing can be thought of as the direction positive charge is moving, even though it's actually negative charge moving the other way. But if you imagine this as positive charge moving this way, that positive charge ends up building up on this plate. Any other questions on that so far? So if we're assuming the capacitor is full, that means that it has finished charging. There's no more current flowing through that branch. Because if there was still current flowing, we would assume that it's not full yet. It's still in the process of charging up. So fully charged capacitor, we would assume current through that branch has stopped. And if we redraw the circuit with that in mind, we now know there's no more current flowing through this branch. This branch is effectively a dead end, which means it essentially acts like an off switch. It acts like a break in the circuit. In the same way that the empty capacitor acted like a short circuit, just wire, a full capacitor acts like a gap, just a break in the circuit. Because a full capacitor does not allow charge to pass, does not allow current to flow. So the full capacitor acts like just a gap, a break in the wire. Which means since we know there's no current flowing through this branch, we can just ignore this branch entirely. So no current at all flows through the capacitor. Is there still a path for current to flow in a loop though?
So there's no current flowing through the capacitor.
Right. Is there still a path for current to flow in a loop though?
Yeah.
Yeah, we still have a path from the battery through resistor 1, and the current's going to split and then join back together. So we do have a loop. In fact, we've got a loop with this parallel split in it. And we can analyze this loop, ignoring the capacitor entirely, because no current is flowing through that branch anyway. We can analyze this loop in the same way we did for any situation where you've got this sort of arrangement: battery, resistor, and then resistors in parallel. And so we could do that as usual, first by finding the total equivalent resistance. And what would the total resistance here be? If you combine the 4 and 2 in parallel, what does that become? If we've got in parallel, so 1 over 4 plus 1 over 2, and then invert the result. What does that turn into?
4 over 3?
Yeah, because we got 2/4, or 1/4, 2/4 is 3/4, so that becomes 4/3. So these two together act like 4/3 ohms. That's in series with the 3 ohm resistors, so we can just add those together. So that would be 4 1/3 ohms, or as an improper fraction, that would be 13/3 ohms. And note that that's very different from the total resistance before. When the capacitor was empty, these resistors were shorted out, so the total resistance was 3 ohms. As the capacitor fills up, the total resistance matures to 4 1/3 ohms. So the total resistance has increased as the capacitor fills up. The general shape of the charging and discharging graphs. Yeah, let's take a look at the shape of the graphs once we find the final values as well. So with the total resistance, we can now figure out the current. If we go back to the usual delta V equals negative, or epsilon minus IR equals 0. So current is going to be epsilon divided by R, specifically epsilon divided by R total, if we just care about the current through the battery. So epsilon, 40 volts, divided by 13/3 is the same as multiplying by 3 over 13. So we get 120 over 13, which is probably like 9 and something. 9 and 3/13, I think. Yeah, that seems about right. So that would be the current in the main loop here. Let's say we call that I1. I1 would be 120 over 13 amps. So that's the current in the main loop, 120 over 13 amps. And what's going to happen to that when it hits the junction?
It's going to split up.
Yeah, it's going to split up. And we could use the usual approach of, we know that this battery adds 40 and this resistor is going to subtract current times resistance. So 3 times 120 over 13, and then figure out how much is left. But another way we can do this as sort of a shortcut, what do we know about the values of I2 and I3 already before we even do any further calculations?
They're the same?
Do they have to be exactly the same as each other?
They add up to I1.
Yeah, we know they have to add up to I1. I2 plus I3 must equal I1 based on the junction rule. The 120 over 13 coming in has to split into I2 and I3. But we would only expect it to split evenly under what circumstances?
If the resistors were the same.
Yeah, if these are the same resistance, then it would split evenly. They're not the same though. One of them's 4 ohms, one of them's 2 ohms. So if the top resistor is twice as much resistance, what should we expect about the current?
It should be half as much.
Right. Twice as much resistance means half as much current. So I2 should be exactly half of I3. Or to put it another way, I3 should be exactly twice as much as I2. And we can use this to solve algebraically for the currents without even messing around with voltages. If we just say that we know that I1 plus I2 plus I3 must equal I1. And we also know, because of the resistances, the ratio of resistances is 2 to 1, so the ratio of currents has to be 1 to 2. I3 has to be exactly twice as much as I2. We can make this substitution. I3 can be just replaced completely with 2 times I2. And with that substitution, we can now combine like terms and get what on the left side? What's I2 plus 2I2?
3I2.
Yeah. So that means 3 times I2 equals I1. So I2 is going to be 1/3 of I1. And then I3 is going to be twice that much, so that'll be 2/3 I1. So this incoming current goes through a 2/3, 1/3, or 1/3, 2/3 split, because 1/3 is half of 2/3. So 1/3 of I1, 1/3 of 120 would be 40. So 40/13 amps. And then I3 would be twice that much, so that's 80/13 amps. So we now have all three values of current. We know I1 is 120/13 amps, I2 is 40/13 amps, and I3 is 80/13 amps. And this is, of course, after a long time, once the capacitor is full. Any questions on that so far?
So in general, when you have a capacitor, then the current that leaves the battery would be higher because there's less resistance it has to encounter, right? And then once the capacitor fully fills and like nothing can go through it, and I guess thus there's more resistance the current has to go through, then it would be smaller when it leaves the battery. Right?
Yeah, because the capacitor filling up means that the capacitor blocks current through that path. And in general, anytime you cut off a path, anytime you restrict the number of paths available to the current, that increases the overall resistance. Even though we haven't changed any of the resistors, all we've done is open or close paths. But restricting the situation so there are fewer paths available means the resistance overall increases. And more resistance total means less current. So the current through the battery is going to be decreasing here. Yeah, because originally we had 13 1/3 amps of current through the battery. Now we have, I think this worked out to 9 3/13. So that is weaker. Any questions on that so far? So at this point, we have starting and ending values for all the currents involved. So we can actually make a graph of all the currents. So let's try that. Looking at current one being through the battery, current 2, and current 3. And we could also even look at current through the capacitor. So we've really got 4 currents involved here. We've got current 1 through the battery and resistor 1. We've got current 2 through resistor 2. We've got current 3 through resistor 3. And let's also say current 4 through the capacitor. And we want to look at the initial and final values of all 4 of these. So current 1, the current through the battery, started at 13 1/3 amps and ended at 120/13, which is 9 3/13 amps. So that has decreased. What about the current through the resistors, resistor 2 and 3? How much current did those have at the beginning?
0.
0. When the capacitor was empty, current only traveled through that path. Resistors 2 and 3 were shorted out. So resistors 2 and 3 start with 0 current. But after a long time, they now have 40/13 amps and 80/13 amps. 40/13 is, I think, 3 1/13, and this would be 6 2/13. So those are the final currents through each of those paths. Any questions on those values so far? And then the capacitor, in the original circuit, the capacitor was part of the one and only loop we had. We had current flowing through that one loop and nowhere else. So originally the capacitor's current was the same as the current through the battery in R1. But after a long time, what was the current through the capacitor? Once the capacitor fills up, how much current does it get?
0?
Yeah, no current at all. Because at the beginning we had 13 1/3 amps of current flowing through the battery, R1, and the capacitor as just one single loop, and no current at all flowing through current or through resistor 2 or 3 because those branches were shorted out. After a long time, we have a weaker current flowing through the battery because cutting off a path leads to higher overall resistance. And that current splits 1/3 and 2/3 through these two branches. And then none of the current goes to the capacitor because it's so full, it's blocking current from flowing. Any questions on those values so far? All right, so let's try actually graphing these. Now that we have these starting and ending values of all the currents involved, we can try graphing these. If we're graphing time versus current, and I'm just going to mark some of the important values here. It looks like 3, 6, 9, 13, or a little bit off from those. So I'm just going to mark this in 3s. So in terms of starting values, we know that we have, let's say, battery and R1 start off at 13 1/3. And current 2 and current 3 both start at 0. And then the capacitor's current also starts off at 13 1/3. So at the very beginning, I1 and I4, the current through the battery in R1 and the current through the capacitor both start at 13 1/3 amps. And current 2 and current 3 both start at 0 amps, no current at all. But the final values, what would the final values signify on the graph?
Like when the capacitor is fully charged.
When the capacitor is fully charged. Is that ever actually going to finish happening? Will the capacitor ever truly be full?
No, it would like reach an asymptote of some sort, right?
So these final values are not values that it actually reaches. Those would be instead the asymptotes they're approaching. So for instance, current 4 starts at 13 1/3 and approaches 0 as an asymptote. So we've got 0 as our asymptote. The curve for I4 is just going to approach that asymptote, the current through the capacitor. And likewise, current 1 starts at 13 1/3, but approaches 9 3/13. So 9 3/13 would be about here. So current 1 starts here and approaches this asymptote. And then current 2 starts at 0, but approaches an asymptote of 3 and 1/13. 3 and 1/13, about here. So current 2 starts at 0 and approaches this asymptote. And then current 3 starts at 0 and approaches 6 and 2/13. This asymptote. So these would be the currents involved here. Any questions on that so far? Or any other questions about that circuit in general? And of course, if you want more accuracy on this, if you knew the half-life and or time constant, you could mark those as points on a time graph. Like let's say the half-life, 2 times the half-life, 3 times the half-life, and so on. And each half-life, you're just going halfway towards the asymptote. Yeah.
So with time constants, I just wanted to clarify, but basically like after each time constant, the current like decreases by 1/3, right? Like around.
It's not exactly 1/3. It's more. It's
like around
to about 37%.
Okay.
Specifically 1/e of the original value.
Yeah. Okay.
But that's not necessarily 1/e of the original amount. It's 1/e of the original difference. So for example, we know I2 is going towards 6 and 2/13. I2, or let's say I3. I3 starts, if you want to focus on just that one, let me draw out just, actually let me use some easier numbers to work with here. Let's say we've got a value that starts at 2 and is approaching 10. So if we have a value that starts at 2 and is going to approach an asymptote of 10, how far below the asymptote is that right now? If it starts off at 2, how far is that from the asymptote?
It's 8.
Yeah.
Yeah, I think I understand that. Like you would just look at the difference because the asymptote doesn't always end up at like 0.
Right. We're basically measuring everything from the asymptote. So after one time constant, you take that difference and divide it by e. So you'd be 8/e below the asymptote. 8/e is going to be 8, about 1/3 of 8, a little bit more than 1/3. So maybe a little more than 2 2/3. Specifically 8/e from the asymptote. And then if you go one time constant further forward in time to 2 tau, we're going to divide by e again. So if you've got 8, and then you divide by e, you get 8/e. If you divide by e again, what would you get?
So the amount that decreases after each like time constant is like the difference divided by e?
The difference is what's decaying, which is why we still call this exponential decay, even though it's an increasing function.
Okay.
The function's value is not decreasing, but the difference is decreasing. So you divide by e again, and the e in the denominator becomes e squared, because we're just dividing by e again and again. So at this time, the difference is going to be 8/e squared, which will be even smaller. And then one more time constant into the future at time 3 tau, you'd now be only 8/e cubed below the asymptote, and so on. But once you've got a few data points, and it's possible to do time constants and half-lives on the same axis if you want to have even more data points. So you could graph like tau, 2 tau, 3 tau, and also the half-life, 2 times the half-life, 3 times the half-life, to get more data points. Once you've got enough data points to see the pattern going on, connect those with a smooth curve approaching the asymptote, and there's your graph. So the whole idea of time constant and half-life is basically a way of getting even more detail. So you know approximately how much time it takes, rather than just saying, well, we know it's going to approach this asymptote, but we don't know how quickly. The time constant and half-life tell you how quickly. Any other questions on that? And if you want to get some more practice with just exponential decay in general, I put up a couple of questions on mathandcheese.org. If you just go to math.andcheese.org/P7B, scroll down, there should be a page, a link to a page with a couple of more problems about exponential decay. They're talking about in terms of fluid flow rather than electrical circuits, but the math is still the same. So take a look at those and give those a try if you want to get some more practice with just exponential decay, time constant, half-life, the equations, and the graphs. Any other questions before I go? All right, see you next time.